Right, welcome everyone to our third session on understanding and using radar data. Thanks all for joining us today. Just a reminder that these sessions have been organised by JNCC as part of our Copernicus User Uptake project, and that's funded by the Caroline Herschel Framework Partnership Agreement. Quite a few of you have emailed since last week to say how much you're enjoying the sessions and finding them useful. So I just wanted to say thank you very much, because it's really been nice to have the feedback. I have put together a brief online feedback form, which I will circulate during Wednesday's session, and I'll also sent out via email. So we're going to start today's session with another guest speaker. We've got Katie McPherson from the Marine Management Organisation, who's going to tell us about how the MMO are using SAR data for detecting vessels at sea with the aim of monitoring and tackling illegal fishing. So if you've got any questions for Katie, please could you type them in the chat, and then we'll deal with them at the end of the talk. Then after Katie's talk, we'll hand back over to Professor Iain Woodhouse to deliver the rest of the session. We're going to look at the vegetation and forestry signals from radar data, and talk about how radar builds an image and some of the unique challenges of radar data, with finishing up with a bit of a look ahead to Wednesday's practical session. So as before, please could you keep your webcams and microphones off during the talks, and please do keep putting any questions for Katie or Iain in the chat as we go along. So I'm going to hand over to Katie now, and just say thank you very much for accepting our invitation to talk to us today. Thanks, Katie.
Okay, so afternoon everybody. My name's Katie McPherson and I'm Head of Compliance and Enforcement for the Blue Belt programme. So what I wanted to talk through today was how we use SAR and other Earth observation data from an operational side of things. The Marine Management Organisation are very much end users. We don't have any in-house analysis. So these training courses have been really good from our perspective to help build our understanding of it, because really we only see the kind of outputs of what we need to use. So what I'll just start talking around is giving a bit of a background to the Blue Belt programme, and then talk about how we use satellite surveillance to tackle illegal fishing. So the Blue Belt programme is a 4-year programme. It's been recently extended for an additional year, and it's funded through the Foreign Commonwealth and Development Office and DEFRA, and it's delivered jointly by the Marine Management Organisation, where I'm based, and CFAS. So the idea of the programme is to protect 4 million square kilometres of water across 7 UK overseas territories. There are 14 overseas, UK overseas territories in total, all of which I had to Google before I started this job, and we work with 7 of them. So that's St Helena, Ascension Island and Tristan da Cunha in the South Atlantic, South Georgia and the South Sandwich Islands, and the British Antarctic Territory in the Antarctic, Pitcairn in the South Pacific, and the British Indian Ocean Territory. So the programme looks to implement marine protection strategies, and it takes a really holistic approach. So from the scientific research and evidence side of things through to implementing management measures, right through to supporting compliance and enforcement. As my job title suggests, I focus on the compliance and enforcement side of things. And one of the threats facing the UK overseas territories is from illegal fishing, or IUU fishing, which is illegal, unregulated and unreported. So the image in the bottom right shows an example of what an illegal fishing vessel might look like. Not particularly pleasant place to live or to work, but they can operate on the high seas for months or years at a time. They transship their catch at sea, refuel at sea, and it can be really difficult to track and trace their movements, especially if they tamper with their positional systems. Equally, the provenance of the fish that they catch can be really difficult to identify. So when we're talking about illegal fishing, in this case, we're talking about those vessels which aren't licensed or registered to the overseas territories. They're operating on the high seas, and they tend to cross into overseas territory water at that 200 nautical mile territorial boundary, some miles away from land. They fish in overseas territory waters without a license, and then disappear again. It's worth also flagging some of the challenges of working in the overseas territories. For those who might be used to dealing with fisheries from a European or UK perspective, it requires a really different approach. And the first thing to highlight is just the spatial scales that we're talking about, huge areas of water. In total, we're talking about 4 million square kilometres of protected waters, and that diagram on the right kind of gives an idea of what that might look like if it was UK based. But even when you're looking at individual OTs, there's still vast areas. The British Indian Ocean Territory has 640,000 square kilometres. Pitcairn has a marine protected area of 830,000 square kilometres, and South Georgia and the South Sandwich Islands have an MPA which is like a whopping 1.2 million square kilometres. The OTs are also really remote, and they're incredibly small, with small populations, and with that it means limited resources both in terms of time and assets. So only 2 of the OTs that we work with have patrol vessels, but even with this, even with a patrol vessel, that kind of more traditional way of monitoring your fishery, when you've got 1.2 million square kilometres to monitor, you really need to look at a different way of doing it, and that's why we've started looking at satellite surveillance. So satellite surveillance, in this case SAR, and automatic information systems, or AIS, provide us with the most comprehensive coverage of OT waters at the moment. Before I come on to satellite surveillance, and I will get there, I think it's important to explain what AIS is, because the two of them really go hand in hand. For those of you who aren't familiar, AIS, or Automatic Information System, is a vessel-based system which has been a SOLAS requirement since 2002. It's a key piece of arsenal for compliance and enforcement in the marine environment, and it's integral to the work that we do. AIS publicly broadcasts unencrypted radio signals as a safety feature for vessels to avoid collision and to enable authorities to monitor vessel traffic. Each broadcasted AIS message includes vessel identity, gear type, speed, heading, and location. If a vessel has its AIS switched on, it can provide us really good information for identifying vessels in that area, so it can support compliance and enforcement, but it's not infallible. It can drop out for a variety of reasons, which may be due to interference if a vessel is far from shore or satellites aren't overhead. The image in the top right-hand corner shows gaps in AIS reporting. And it can also be tampered with. It can be tampered with to show vessels in different locations to what they actually are. And it can show up incorrect names or old names. The biggest drawback is that it can simply be switched off. And that's where we've started to use SAR surveillance to help identify these vessels which are switched off their AIS and are operating as dark vessels. So the Blue Belt programme and the MMO have set up a centralised surveillance and intelligence hub to provide intelligence to the OTs and help support them in their compliance enforcement actions and decisions. So over the course of the programme, using a variety of intelligence sources, including Earth observation data and other sources, we've built up quite a good understanding of the illegal fishing picture across the OTs. And as such, we've developed risk profiles to help include the type of fishing, key locations, seasonality, that type of thing. And we use SAR surveillance in 2 different ways. The first is to help monitor that risk and kind of ground truth what our understanding of it is. And to do this, we work with Ocean Mind, which was previously the satellite catapult, to monitor key areas at appropriate times across the overseas territories. Ocean Mind will procure SAR images and corroborate them against AIS and other sources to feed into and monitor our understanding of those risks. It's generally quite intense surveillance over a period of time, anything from kind of a month up to 6 months, depending on the area and the location and the risk. It's worth saying, as I kind of mentioned before, that MMO doesn't have any internal expertise in this to analyse the SAR surveillance images. We very much see the end product. Though our AIS analysis is quite sophisticated, we're very much a kind of end user of the service. The second approach is much more of an intelligence-led approach, and for this we work with EMSA, which is the European Maritime Safety Agency, and their operational support services. So in this case, it's much more of an intelligence-led response. So particularly where we've got intelligence that there may be a dark vessel operating, we can request an image from EMSA in a specific location with quite a high turnaround to try and corroborate the intelligence that we already have. We also might use the EMSA service to help us support patrol vessels. Again, as I said before, there's only a couple of OTs that actually have patrol vessels that we work with, which is the British Indian Ocean Territory and South Georgia. And we can use satellite surveillance to help them make decisions about their planned patrol route, or see if there's potential illegal vessels operating where they're planning on going, or it might help determine whether they change their routes to go and intercept them. So this kind of use of SAR surveillance is much shorter, much less intense for shorter time periods, but with a much quicker turnaround than what we do with Ocean Mind, which is that kind of intense, longer period of time, slightly more blanket coverage. So SAR surveillance is hugely important for us from a compliance enforcement perspective. It can cover vast areas, which is obviously essential with the overseas territories. And more importantly, it's not a vessel-based system. So it offers us that ability to identify vessels which have switched off their AIS. However, there are limitations and challenges with it. The first is cost. So we primarily use commercial satellite imagery, which, especially when you're looking at those kind of longer and more intense periods, can be eye-wateringly expensive. Although we do use the Sentinel image services, they don't tend to have the resolution to detect the vessels that we're trying to see. And also, in some cases, the pass rate is quite low as well, so it would have to be supplemented with more with commercial satellite imagery. Weather activity, icebergs, and other natural phenomenon can also give false targets. The image in the top right shows South Georgia, where icebergs unfortunately abound, and those white dots show images which have shown as potential vessel contacts. And if that was the rate of illegal fishing in South Georgia, we would have a few issues. Small wooden hulled vessels or fiberglass hulled boats are also really difficult to detect, and with SAR imagery. Generally, for most of the OTs, it's not a huge issue. The remoteness is actually a benefit. It's much more challenging to get to them, and they tend to need larger metal-hulled, more robust vessels that can actually reach them. But in the case of the British Indian Ocean Territory, these small wooden-hulled vessels that you can see in that bottom right-hand picture make up the majority of the illegal fishing fleet. And that's generally due to their relative closeness to neighbours of India and Sri Lanka. Also, unfortunately, because of this, it does make the British Indian Ocean Territory probably the highest risk of all of the OTs that we work with in terms of the number of incidents of illegal fishing. It's really important to state, and I think it's probably stating the obvious, but SAR images can't positively identify a vessel, and that's really important from a compliance and enforcement point of view. They can show that there's a threat and that there is something there, but without AIS or other corroborating information, it only shows that there's something there. It can still be used for risk profiling, and it's really important actually in some ways to show you what isn't there as well, so it can help target assets and make sure they're deployed more effectively. But what it doesn't enable us to do is take an investigation any further, to contact flag states and to try and further the enforcement process. Even with that AIS corroboration, what we don't have with both AIS and SAR is an ability to know whether or not a vessel is actually fishing. It doesn't show that activity. And again, from a compliance and enforcement perspective, that's a key piece of evidence that's needed. You know, that ability to show gear in the water of a vessel operating within the OTs is something that's key to us to be able to pursue effective enforcement action. But there are a number of ways that we can try and address some of those challenges. So for example, with the small vessels in the British Indian Ocean Territory, we commissioned some work to try and determine whether SAR, in this case RadarSat-2, when used with extra fine beam, could detect those smaller vessels. And there were still misdetections linked to either the vessels being on the edge of the SAR image, the angle of incidence, or having a fiberglass hull, which reduced, but the confidence was significantly increased, and we can now detect around 70% of those vessels. So knowing those parameters that we operate in has been really helpful in that area. Icebergs have been slightly more challenging. Looking at the size and shape is a determining factor to decide between an iceberg and a vessel, but really it's persistence and looking for repeated detection over time. Icebergs drift and they can be modelled, and looking to corroborate them against other sources, both Earth observation and otherwise. I will just quickly mention some of the other Earth observation sources that we use to support corroborating the SAR data. As mentioned, we do often look at the Sentinel-1, where we may have a potential detection and it can provide corroborating evidence. We'd also look at VIRS, which is the Visible Infrared Imaging Radiometer Suite, which can detect light from a vessel. It has been quite successful in detecting squid jiggers in South America, which tend to fish at night using light. But for the fisheries that we primarily observe, we get too many false positives and the confidence is just too low for it to be a useful standalone tool. But where we do have a potential SAR image which shows a dark vessel, it can provide quite good corroboration. Similarly, optical as a standalone tool is too limiting. The footprint is too small, and when you're looking for a small moving target in large areas of water, it's like looking for a needle in a haystack. Also, specifically with Sentinel-2 optical, there isn't that level of automation, so it requires a significant amount of human resource to look at a lot of empty ocean. But again, where we have a potential detection of a SAR vessel, it can be great corroborating evidence. We also have to look at wider technology as well. So for example, we've been looking at drones which can be launched from vessel patrols. The video and the cameras from these can provide the all-important evidence of gear in the water. So it just provides that other strand of information and intelligence that will help us take compliance and enforcement forward. We've also been looking at passive acoustics and other tethered platforms and sensors. SAR has also helped us identify other sources of intelligence. So for example, it's helped us identify routes of passing yachts and other vessels, which we can now look at working with them to provide routine vessel sightings. So it has provided that broader intel picture as well. So in summary, it's really difficult to monitor and to have effective surveillance and compliance and enforcement across the overseas territories. But there are a lot of different opportunities, and it's from our perspective, it's about using the Earth observation data and SAR along with the other tools to bring together a picture that we can respond to. And I think at the moment we've got fairly good confidence that we have good coverage and we do understand and can respond to illegal fishing that's in the overseas territories. Thank you. I will.
Thank you. Thank you very much, Katie. That was a really interesting talk. And it's really nice to hear like a practical example how you're using SAR, and really good to have a marine example as well. So thank you very much for that. I don't know if anyone has any questions for Katie, or indeed any comments or about how some of the challenges that she's discussed might be dealt with. Please can you put them in the chat? And I think that would be also okay to do any time throughout today. Come back to them at the end as well. You're here with us till the end, Katie?
Yes.
Yeah, so perfect. Yeah, so please do put any questions in. There's nothing coming at the moment. I did have one question I wanted to ask. So on the like analysis of the SAR data and then looking for corroboration between SAR and AIS, how much is that automated? Is that fully automated, or is there some kind of human factor of, like, say, deciding if it's a boat or an iceberg?
So in terms of SAR and detecting vessels and AIS, there is a level of automation there. but it does still require an element of human analysis. Certainly from the kind of, I think with icebergs is probably an increased one because of the time that's required to look at it. But yeah, there is increasing automation with AIS.
Okay, thank you. There's a few questions that have come in now. Mike has asked, there's Mike from Natural England, how about similar approaches in the UK? So you're looking at this in the overseas territories. Are you looking at anything in the UK at all?
So the UK is very different. We don't have illegal fishing in the same way that we have in the overseas territories. You know, those kind of vessels just encroaching in territories which have switched off all their positional systems. Generally, we've got a relatively good idea from vessel monitoring systems that all vessels are required to have an AIS where they are. So it is different, but we have been using it more. We've certainly used we certainly kind of had a proof of concept this time using some Earth observation data when all of our marine officers were in lockdown, and we were using it to see whether vessels were staying in port, and that worked really well. So I think going forward it'll increase, but it's a very different way of operating in the UK, and we've got a much clearer picture of vessel movements.
Okay, thank you very much. I'll just bring back a hand over to Iain to carry on with the session. But I'll just do one last question. This is coming from Helen Lillis, who's a marine mapper at JNCC. She says, you use commercial data because it's higher resolution. Is that data from commercial satellites or commercial companies processing the same data to a higher quality?
I don't know. Sorry. I don't know the answer to that one.
I think it's, is it, so you've mentioned radar sats too as one of the other platforms that you're using. Yeah, so, so you're using some commercial satellite platforms and sensors, and rather than Sentinel-1, which was maybe a slightly lower resolution.
Yes, it's I think it's that Sentinel is is a much lower resolution for us to be able to see the vessels. So I think it's probably the data from the actual satellites rather than the processing.
Yeah,
but don't quote me on that.
Yeah. Well, we can hand over to Iain to comment on the possibility or other ways of processing data to a higher spatial resolution.
Yeah, I was going to jump in there. Yeah, the default interferometric wide swath mode in the on Sentinel, it wouldn't get you as good spatial resolution as the stuff that you're looking at on the radar sat. So I think it's the former, Helen. So it's basically higher resolution. But I was also going to ask just what latency you need on that. Do you also need it really fast, or is it do you need it within 24 hours of the collection, or do you process it historically, just looking at trends?
So both. So we kind of have that. We've built up risk profiles over time, which we monitor in kind of we kind of have that blanket coverage, which can be much slower time. But if we're responding to intel reports of a dark vessel, we'll look at turning it around really quite quickly, especially if we've got patrol vessels out there to try and intercept. So that's where we have Ocean Mine tend to do the slower time, and EMSA can turn around images quite quickly for us.
Okay. Sorry, EMSA? Who's that?
Sorry, that's the European Maritime Safety Agency. So they'll do they'll provide a lot of support for European countries for kind of pollution response, for maritime security, which is kind of what we're looking at. But again, that's commercial data that they're turning around.
Right. I'm going to show. I'm actually going to segue a little bit into Paula, just to let you know. I thought it's actually a good point to pick up, because there's a marine example I'm going to use on Wednesday looking at earth blocks. So I could maybe quickly give you that, show you that example, and then lead into just a quick discussion about what's going to happen on Wednesday.
Brilliant, thank you.
I am going to pause for a second on the recording though, because the earth. I'm just making sure that the recording is back on. Right, so we're on to the third day, and what I wanted to look at is vegetation. So we looked at the surface scattering, and we didn't really talk very much about the vegetation component of that as a layer on top of the surface. So I'm going to spend a little bit of time just looking at vegetation, a bit of a bias towards forests because that's my my area of interest. But before we get onto vegetation, one of the interesting things about vegetation is when you get flooded vegetation. And flooding in general is something of interest. And we had Crispin talked about flooding last week in his interesting talk. And one of the interesting things, though, is that as a first pass, if an area starts to look dark, an area on the land surface looks very, very dark, you will assume that it's flooded with water. So there's some liquid water on the surface there because it's scattering the energy away. And in fact, one of the other examples that we'll look at on Wednesday on Earth Blocks is the flooding in Mozambique last year, where you can see the dramatic change that happens when the typhoon comes in and vast areas of the landscape suddenly turn black in the radar image when the area is flooded. But when you've got vegetation, the thing is that you've got this double bounce effect. And last week we looked at the double bounce as being one of these very strong scatterers. It's a strong scatter because it always scatters the energy back in the direction it came from. But it's also has a big impact on a radar image because all the scattering looks like it comes back from the location of the vertical to the horizontal. And the key thing with vegetation is that you can have a smooth surface underneath anyway, which would generate quite a large backscatter. But when it's a water surface, it is very smooth. And the fact that it's under vegetation typically also means that there's not much wind roughening the surface. So you get a mirror-like surface beneath the vegetation. And what you see, the difference between dry season and wet season. So these are some examples that have come from the ESA biomass mission. The preparatory, the biomass mission hasn't flown yet, but you can see in this river here under the forest is that the forested area. So the river is the black meandering line through the middle. It's a large river. It's got a flat water surface, and so it looks black in the radar image because it's scattering all the energy away from the sensor. But when it floods, you don't get large areas of dark area around it. What you get is actually an increased backscatter. It becomes brighter, and that's because the longer P-band microwaves are getting through this vegetation canopy, and you're getting a strong contribution from the double bounce from the vertical trees under the water surface. It's quite important. So this is actually a radar sat image. It's from Belize, and this is a before and after in terms of when there has been flooding. So that's before the flooding, and this is the flooding. And in particular, you can see these large areas of sort of square rectangular agricultural fields that have gone from being having short vegetation on them and therefore looking quite rough and bright to being very, very black because they're now covered in water. And these areas that have these agricultural areas that haven't gone black are either because they're slightly higher in altitude or because they might actually have a higher vegetation cover. I'm just trying to get the, I'm trying to annotate on this. Hold on a second. So the area to look for, I'll just change the color here, is that some of these areas down the bottom. So if I highlight some of these areas that are actually brighter, is that if we, you'll see that these areas of forest have actually become brighter when the flooding has happened. And that's because if you look closely, you'll see in the bottom one, for example, where it's highlighted, there's a little tributary. So what's happening here is that area that's got brighter has probably flooded underneath the forest, and you're seeing a brighter return. And this is just flagging up one of the challenges of especially automatically interpreting radar images, but interpreting radar images generally, is that it doesn't always do exactly what you expect it to do. And it can sometimes be a little bit more complicated because of the multiple interactions between the things on the surface. And typically vegetation is one of the key things that introduces that complexity. And so if you're trying to do flood mapping here, if you just draw around the areas that are now black, that's not actually capturing the full extent of the flood. Is that there are areas that are also flooding beyond that, but it's got a layer of vegetation above it. And so you don't see it as a black, you actually see it as a strong double bounce. Now, in terms of, I'm not going into detail in this course. I'm hopefully, well, the ambition in the time that we've got is that you start to learn a little bit more about the interaction with vegetation, such that you can see that looking at multi-temporal or multi-frequency backscatter is going to give you some kind of information that's going to help you differentiate land cover features. And I'm going to show you one example just to help pick up on that. In that last one, for example, in here is that you might well be able to look over changes in time to identify areas around the river that have flooded forest, for example. And so a multi-temporal analysis of that might extract some of the features of the changes in the land surface. But here I'm just going to look at a quick example. This is from airborne radar, not satellite radar. And that's given me the advantage of being able to have C-band, L-band, and P-band. And so the P-band, if you remember, is the really long 70-centimeter one. So it gets much further through the forest canopy and is therefore much more sensitive to the bulk structural properties of the forest. And when the biomass mission from ESA is launched, you'll be able to get that kind of data everywhere in the world. Now, because we've color-coded that, I'm going to, if I split up those images, we start to see some of the differences. I'm going to pick out some differences here. So this is a color composite, the one that I've just shown, which is a composite of the different wavelengths. So it's a bit more like the kind of color that you expect to see in a color composite for optical domain. But these are not differences in color. They're picking out differences in structure. So this particular area, so you can see the black area. Let me just get the drawing function up. This very dark region at the top, that's the little lagoon. But there's also this very blue area that comes up. And if it's very blue, that suggests it's very bright in the C-band, but very dark in L and P. And the other thing to note is that you have these dark areas that are little savannas, and the brighter strips of the gallery forest that strip through the savanna area. So these are all forests that are essentially, there's a little drainage channel here that supports the some of the vegetation. So if we break it up into its different component parts and zoom, what we can see is that the C-band backscatter, for example, down the bottom here, that area around the lagoon is very short vegetation. It's high reeds, but they're relatively thin compared to the forest area. And so what we're seeing is that the vegetation is being seen differently by the different wavelengths. The shorter wavelengths tend to pick up the smaller bits of vegetation quite well. The longer wavelengths get deeper through the vegetation. So they're typically looking at the ground for longer as you get increasing vegetation. So as you zoom into this area, that's the C-band. The small vegetation, the short vegetation around the lagoon gives you quite a bright signal compared to the L-band, and in fact the P-band is even darker. And so the thing that P-band, or in fact L-band as well, both L-band is available from space. So the Argentinian SOUCOM, the Japanese ALOS pulsar, the potential upcoming Tandem L from DLR, and the NISAR from NASA and India together will be, these are all missions that are creating L-band data, and they're all very good for looking at forests because the longer wavelengths give you a much better correlation with the structural properties. But L-band is even, P-band is even better. The longer wavelengths, it means that a lot of the drier, flatter, non-vegetated or short vegetated areas aren't giving you much backscatter at all. It's all coming from the surface. So let's look a little bit more in terms of forest biomass, or biomass generally, I should say, because I realized that I didn't have anything showing what happens with agriculture. So I thought I should quickly put in a, in fact, let me just quickly change something there. Because I've noticed that they, my poor student, they spell, the automatic speller has turned their name into cheeseburger, and I'm sure she wouldn't like that. So this was a master's student from last year who analyzed some Sentinel data. So this is Sentinel VVVH, and it's comparing it to the NDVI over a period of time going from October through to July. And what you can see here in terms of the radar data is that there are very strong temporal patterns, which are quite different from the seasonal pattern you get from the NDVI. So that's harvesting right at the end. So at the end point, the fields are being harvested. But what we see is, interestingly, initially for the vegetation, as the crops grow, the radar backscatter actually drops, and that's both in the VV and the VV and the VH. So the backscatter signal from the vegetation as it's growing seems to do the opposite of everything that I've been mentioning. And the general understanding of what's happening here is that there's an absorption of the VV signal as it goes through the vegetation canopy. So it's doing much more absorption and not enough scattering. Oops. But then when the vegetation grows large enough, when the seed heads starts to form, the backscatter picks up again, and you get quite a strong signal. So it's certainly possible to use Sentinel data as an indicator of growth patterns, especially when you combine it with NDVI. But it doesn't, just note that for short vegetation, it doesn't necessarily always do what you might expect. If we look at forests, on the other hand, going back to, this is a paper from Mark Imhoff, which is one of the sort of classic early papers in 1995, showing essentially what was at P-band, certainly, an apparent correlation between the biomass, which is what is along the bottom axis here, so the tons per hectare, the dry biomass of the forest, versus the backscattering coefficient. So how bright were the pixels? And what you see is that for P-band, so the longer wavelengths at the bottom here, is that certainly up to about 100 tons per hectare, there seems to be a fairly good correlation between the increasing biomass and the increasing backscatter. When you get to shorter wavelengths, so it's L-band up the top here and P-band up in the top left, is that C-band, sorry, the C-band has almost no correlation. It very, very quickly reaches the point where there's no more sensitivity. And it's this shape and this flattening off. This is what you'll often find in the literature referred to as this saturation. So the saturation of the backscatter. And I'm going to explain, I'm going to give you one explanation for what's happening there. And I mentioned this graph on last Monday. And again, I just urge caution here in terms of interpreting these graphs. And I often make myself quite unpopular by complaining about some of these graphs. The biomass mission is going to be fantastic. It's going to be the first spaceborne P-band mission. It's going to generate data that is beyond doubt is going to change our perspective of radar remote sensing on the planet. It's about the most exciting shift in radar remote sensing from space that there has been probably since the launch of ERS in 1991. But I'm concerned that people's hopes aren't increased too much. So there is some level of healthy understanding about the limits of what we're going to be able to do with a mission like biomass. And one of the key challenges is just the spatial resolution. So going back to the diagram we showed with the limited bandwidth of or the availability of bandwidths in the microwave and radio part of the spectrum, is that the biomass mission has been given a relatively narrow range of frequencies that it can use. And we don't have time in this course, but that limiting the range of wavelengths that it can use, or the bandwidth, has an impact on the spatial resolution. So it's going to be in the region of a few hundreds of meters. It's not down at a level of your standard Landsat 30-meter pixel. The other issue, and I'm going to talk about that in a bit more detail, is that for me, that blue line doesn't really capture the trend in that data. And that blue line has been based on an assumption, and then has been applied to fit that function. So if you look at the blue line, you're kind of distracted by the fact that sensitivity's certainly lost below 200 tons per hectare. The other challenge with this particular diagram is that the argument in the paper was looking at the trends. So what they were trying to emphasize was that there was a similar trend between these different types of forest. But they did make some general assumptions here that implied that they moved some of these points. They moved them en masse, so they collectively moved them to essentially match the line. And so it's not going to be as consistent and as easy to interpret the results from this mission as some diagrams have a tendency to reflect. And one of the things that I want to kind of show you is just some of the and that's the saturation point. So, you know, where does that saturate? We can argue all day about where those points lose sensitivity, but I do want to pick out on some of the not so good examples. And some of these examples, because I'm essentially critiquing them, I thought it was unfair to put the citations. So if you want to know where they come from, I'm willing to give you the citations, but I didn't want to particularly pick on people. So some of them have citations, some of them that I might be less positive about, I didn't put citations in because I'm not trying to pick on individuals, or it's a very cultural thing in the radar community. So, for example, the work that was done in the EMISAR campaign in Sweden is that it's not as convincing in terms of L-band. And there's some reasons why that might be the case here. It doesn't give you quite as good as trend as you might expect. And there's some other work. So the work by Neef and al is actually really good. And what they go on to do is to show that there are other information, like the canopy height is a better indicator of the biomass. So it's a good paper. I encourage you to go and see. But I am conscious of the fact that sometimes people only present the graphs and you don't see all the text that's described here. But if I look at the primary forest points in this data point, what I see is a collection of primary forest points which have no real correlation, and a set of secondary forest that has no real correlation. And that is there's a danger here in terms of how we interpret graphs. And so there's other graphs, for example, that are in unusual circumstances in terms of this data. And I'm going to show you what's called Anscombe's quartet. I don't know if any hands up or thumbs up for anybody that's come across Anscombe's quartet before. I'm having a quick look to see. I don't see anybody putting their hands up. But this is the challenge of how you visually interpret data. So if you go and look up Anscombe's quartet, what you'll find is that you can generate these 4 data sets, and they all have an R² of 0.67. So they all have exactly the same line that fits to this data, and they all have the same R². And I generated a couple of other graphs that I think represent some of the work in the radar community. So that this is an example data set. This is one of them, and all my examples have got an R² of 0.8, which looks really good. And you think if you reported on an R² of 0.8, you would think that was a strong correlation. But if you have 2 clouds of data points, you can get a strong correlation. And so that's potentially problematic. It's also potentially problematic if you have 2 sets of lines. So these data points fitting this logarithmic curve is that you'll get an R² of 0.8 on these data sets as well. but I would argue very clearly that there is a trend here that's not got any correlation and a trend there that's not got any correlation. And so we have to understand what the data is telling us, rather than creating graphs that generate patterns and offer an optimism about how you can measure forest biomass that is perhaps not actually really inherent in the data. So you have to be very careful. And essentially what I'm suggesting is that I don't want you to be cynical about the way that remote sensing and radar, remote sensing in particular, extracts or can determine biomass or is sensitive to the forest biomass. But I would urge you to be cautious about how you use it. And there are very specific cases where it works very well, but there are other cases where it doesn't work very well. So it's not as simple as it first looks. So I want to just quickly give you an explanation of, or one explanation of why you get that saturation. And we can do that through what's called the water cloud model. So the water cloud model is essentially taking our forest and turning it into a collection of random, in the first instance it was random spheres, but the more modern incarnation is what's called the random volume over a surface. So it's randomly oriented cylinders. So you're assuming each of your branches is a cylinder, and you've just made a cloud of these branches, and they're all the same size and shape. And as you get to more and more, as the opacity increases, you get to a point where you can't see through the vegetation any longer. And that's where you're going to get your saturation. And so the other key thing with that is that if you can see further, if your wavelengths are long enough to see deeper into the forest canopy, then it takes longer before you get to that point of saturation. So what I'm going to show you here, this is a little animation, but I'm going to physically show you a kind of an example of what I mean. So I'm going to give you a little animated version of what I'm physically going to show you here. So this is a collection of sort of semi-transparent sheets that I've just clipped together. And what I'm going to show you in this animation is that I'm going to add a collection of sheets, and if I add one sheet, you can still see the background. You can still see the pattern through there. If I add a few more sheets, then it becomes a little bit. You can still see it, but it becomes a little bit more obscured. And as I add more and more sheets, eventually you stop being able to see the background picture, and it just becomes white. And once it becomes that point where you can't see through to the background picture anymore, it doesn't matter how many more sheets I add to that, it's still going to look the same. It doesn't change anymore. And so my little animation is based on just adding these little sheets, except I happen to have colored them green here in the animation. And so what I've got is the equivalent of my text here, which says the ground. And I'm adding a pixel worth of my semi-transparent layer. And up in the top right here, we're looking at the side-on view, so the cross section. So if I add another layer, that's my next layer, and you'll see that it starts to get a richer green color as we add these semi-transparent layers. And so the graph at the bottom is plotting the intensity as I add the amount of stuff. So I've got 3 times more stuff than I did in the first instance now. And if I keep going, I can keep adding layers. And eventually, if you looked very closely, certainly on my screen, probably not through Zoom, I can still just make out the letters here behind the 5 layers we've got. But if I go to here, it starts to disappear altogether. And so as I add more layers, it makes no difference now to the signal. It's as green as it's going to get. I can't see through to the bottom, and that's where you end up with this saturation point, because it doesn't matter how many layers I add anymore. So this is the classic explanation for what's happening when you see the saturation. And if I've got longer wavelengths, then each layer is slightly more transparent. So I have to add more layers before I stop seeing right through to the ground. The one challenge I have with that, and there's only 2 people in the world, me and Matthew Brawley, a former PhD student, who believes that there's another explanation. I don't have time to go into the explanation now, but if you wanted to go and look at some of the work by myself and Matthew, what we were interested in is that, well, trees don't grow like that. Forests don't grow with a homogeneous layer of scatterers. You tend to have a small number of very large cylinders near the bottom and an increasing number of increasingly smaller scatterers as you get further to the top. And so there is possibly a different explanation, and what we found was that the structural properties of the forest had a big impact on the trend and where that saturation, and whether or not there was any saturation. And so I'm not entirely convinced that our understanding of backscatter from forests is complete yet. So we have to, I think there's still some work to be done. But in any particular given context, well, in fact, that was my argument there in terms of progressively smaller scatterers with increasing height into the canopy, and they also become more numerous as you get higher into the canopy. So the key thing is that when you get a fairly regular forest with consistent structural properties, you'll find that you do get very strong correlation in that particular area between the increasing biomass and the increasing backscatter. And that can be a really valuable resource. Whether or not you can take that same relationship and apply it to a different forest, that's less clear. And our understanding of what exactly is happening is perhaps not yet fully complete. But this is one of the things I'm going to look at on Wednesday. So on Wednesday, we'll actually be able to explore some real data. We'll be able to let you explore any data over the entire world for the last 5 years. And you can look at Sentinel-1 data for just about anywhere. And we'll also have pulsar data back for the last, 5 years. So there is an opportunity to look at what the impact is of areas that you know. So it might be areas of forests, or it may be coastal areas or agriculture, but an area that you know and you know well. On Wednesday, you'll be able to go and look at that and investigate very quickly some of the temporal and spatial features in the imagery. And we'll use that as the basis to relate back to the theory, to see if we can use the theory to help interpret what's going on. Right, that's 3:05. So what I'm going to suggest, a very quick, let's say 2-minute break, just a comfort break to rest my voice apart from anything else. You can go quickly put the kettle on or something. So we'll go, it's just about to turn 7 minutes past. So let's say 10 minutes past, I'm going to start again. And again, this is also a chance for me to check if you've been putting in any questions in the chat, and I will answer them. So if you do have questions, stick them in the chat now and I'll answer them before we start again at 10 past. Okay, that's 10 past, so hopefully everybody's back. I should have encouraged you all also just to get up and walk about. It's I actually have a piece of software on my computer that every 40 minutes it tells me I have to walk away from the computer and something else, which is something I would encourage you all to get something, especially in these days where we get up and sit in front of our computer all day and then leave. So it's important to step away from the machine at some point. Right, I didn't see any questions, so I'm just going to crack on. And we're going to look at the imaging geometry and the consequence. The key thing that I want to talk about imaging geometry is because it's very, very different from optical sensors. And I'm anticipating you're going to have one of two reactions to these slides that I'm going to share with you over the next 45 minutes or so. Some of you are going to cry in dismay at how incredibly complicated it looks of how an imaging radar system actually works. And you're going to say, can we just forget all this stuff and go straight to the image interpretation on Wednesday, please? Because I don't really care how they make the image. I just want to look at some images. And that's a valid response, and I don't have a problem with that. But the one thing that it is advantageous for you to understand some of the complexities of how radar works, because it has an impact on some of the features of the image, and therefore it's important you kind of know where that comes from, and it will help you to interpret the imagery. The other reaction some of you will have, which is certainly my reaction, is that wow, isn't radar just the most incredible imaging system you could possibly imagine? It is so a combination of complexity, but a fantastic set of problem solving that generates images of very high resolution at incredible distances, using signals that are incredibly low and barely measurable above the noise sometimes. So I'm guessing you're going to have one of those two reactions, and certainly do drop me a line or let Paula know, or in the feedback. It'd be great to know which of those responses that you get once you start looking at how radar works. Now, we introduced on last Monday just the idea of echolocation, and the idea it's a pulsed system. So we're going to send out pulses, and they have a finite length, and the rate is going to be given by the pulse repetition frequency. And so I'm going to use some audio analogies today. So I've got a little metronome that I've got a little metronome that I hope is going to work. That is going to, just to give you an idea of the fact that we've got a pulsed system, and that it is sending out pulses and coming back at, and we're measuring the echoes as they come back. Let me just try that again. There we go. Increase the volume so it's loud enough. So that's what we're going to do in terms of, and the measure of how fast we change that is the pulse repetition frequency. So if I increase the rate, that's a higher PRF. It's a higher pulse repetition frequency. And so that's actually going to be significant for us later on, because it makes our life very much more complicated in a radar system. And what we measure is the time delay of the echo. So we're not measuring angles, we're measuring time delay, and we're trying to change that into some feature about the ground surface. So we have our little animation, which are a principle of echolocation. It bounces off the target, it comes back, and we measure that signal, and the time delay of that signal, importantly, and that's going to give us an indication of the range, and we're going to measure the range really, really accurately. But you'll see that this beam is very large because we can't do narrow beams. We need to make very large antennas here in order to make narrow beams, and we're not going to do that. Now, if you take that system and you point it down the way, we've got what we call an altimeter. And an altimeter sending the signal directly below to nadir will give you a very good measure of range. And in my normal radar course, we spend a bit of time actually looking at altimeters in a bit more detail because they're fascinating systems in themselves. Over oceans, you can start to measure average variations in ocean height in a scale of centimeters, and you can measure the accumulation across Antarctic and Greenland, for example, down at scales of centimeters per year as well. And so altimeters are fantastic systems, but they don't generate high definition images because the angular instantaneous field of view is based on the size of our antenna, which is d. So d is the diameter of our antenna, and lambda is the wavelength. And we are about 6 orders of magnitude larger wavelengths than we are in the optical domain. So we've got a problem there in terms of trying to get very, very fine beams. If we want to scan an altimeter type system and make that a very narrow beam so that we can scan the ground and get images on a scale of about 30 meters, is that we need to increase the size of our diameter. So our antenna or our aperture, we need to make somewhat on a scale of many kilometers. And that's going to be physically just too difficult to do. So we're not going to make very large antennas. We're going to have to do something smart instead. So what we do is we take advantage of the fact that we can do range measurements really, really well. And we'll just look off to one side. So we'll look obliquely. And by looking obliquely, it means that our signal coming back is roughly in proportion to our distance along the ground. So we looked at this last week, is that we've now got a system whereby we can take advantage of what we're really good at doing in radar, which is the timing measurements. And we can relate that to a feature. I'm just trying to get my annotation up. We can relate that to features on the ground because we make an assumption about the ground being flat. And if the ground is flat, so in fact, in countries like the Netherlands, you don't have to worry too much about that assumption because it's quite a good assumption that the ground is flat. And therefore that the signals coming back over time are proportionally the time of the targets in, I'll rephrase that. By looking at where the targets are in our time domain, it corresponds well to the distance along the ground. So the antennas that we do use, this is an image of Sentinel-1, and the big panels across the top are the solar panels because we need lots of power. So one of the challenges of all radar systems is that it's always an order of magnitude larger in terms of size and power compared to optical systems because we're transmitting our own energy. So we need to be able to collect lots of power. It's also one of the reasons why we end up with a dawn-dusk orbit rather than a day and night orbit. So it's still a sun synchronous orbit that you tend to put radar systems in, but you put them into an orbit where the local solar time is 6 a.m. and 6 p.m. because then you're actually always, the satellite is always in sunlight, and therefore it's always collecting energy from in the solar panels. A typical optical satellite will have an orbit that's 10:30 in the morning, and 10 or 10:30 in the evening. So it's a sun synchronous orbit, but half of that orbit is in darkness and half of it is in sunlight. We don't need to worry about the sunlight for radar, so we'll have our sun synchronous orbit, which is actually perpendicular to the plane of the orbit is perpendicular to the sun, and then it's always in sunshine. It's always generating power. But the antenna, the radar antenna is this big thing at the bottom. 10 meters or so is always a good way to think of it. About a meter in height. We can look up close to that if we, in this image here, there's some people down the bottom left, so you get an idea of the scale. So that's about 10 meters long. So it's a big antenna. It's going to generate lots of as much power as we can collect in our solar panels. So it's not like a lens anymore. It is just our big collecting device, like our ears. Now, one of the key things that you're all interested in is what the impact of the geometric distortion is on the image. So in the first instance, we're just going to keep in this plane of these animations where we're looking in the range direction. So that's our aircraft flying out of the board. It's looking obliquely. And we had this diagram last week where I was referring to the fact that, well, we're assuming that we've got a flat surface here. And what we're doing with our range measurements, so this is our slant range. That's not the real range. It's not the real distance across the ground. It's the real range that we measure in terms of the signals. But what we do is that we project them down onto a flat surface. So this is our reference surface, or our datum. And if we make the assumption that it's flat, what happens is that our image looks. And if you look obliquely, your optical image is distorted also. Your optical image is distorted in that these pyramids look like they're leaning over, but leaning away from you, whereas the pyramids in the radar image seem to be leaning towards the sensor rather than away from it. So and that's because you're looking obliquely. What we'll find is that these days, actually, there's nowhere on planet Earth that we don't have a good estimate of the topography. The shuttle radar topography mission, for example, covers about 90% of the land surface and gives you 30-meter resolution. There's a little bit of a bias because of the vegetation on top, and it doesn't work perfectly in all the areas where there may be radar shadow or areas of layover. But as a general rule, all of those gaps have been filled in now for the SRTM data. So we don't have to rely on that assumption of the ground surface being flat, and we can say, well, actually, what happens if I take my first guess of the ground surface from SRTM, say, and then use that as my new reference surface and project all the data points onto this topographic surface instead. And if I do that, I'm doing essentially a geometric correction. I'm correcting the distortion caused in my image, and I'm putting the points back into their proper geographic location. You still have problems with layover, and you still have problems with the foreshortening, and you have problems with shadow because there is no data in there. But it's going to make life a whole lot better if we can do that. So that's one of the things that you'll do in the practicals on SNAP. You don't have to do it in the EarthBlocks practical because all the data has been geometrically corrected already, and it's all in analysis ready data format. And just if you've gone to the intro-to-radar.com, you'll see that there's one of the examples that show you the problems of foreshortening and layover. And this is the extreme case here where the top of the pyramid, this echo comes back first before the near side bottom of the pyramid. So it gets located nearer towards nadir in the image than it should. At least C and D here are in the right order. So B and A have been switched around. At least they're in the right order, but they're being squashed up. And that's because we're measuring as a function of time. If we then track that back to mapping it onto a topographic reference surface, we'll get a much better result. And here's a nice example. This is just an island in the Caribbean showing you what it looks like visually when you have that layover or the foreshortening effect. Is that if you look closely, you can see that you get these, it looks like they're all leaning. It looks like a geographical feature of some kind of layering, but it's not. It's because this has been imaged from the left, and all these mountain peaks look like they're leaning towards the sensor. So let's look at a bit more detail about what it is we want to do here. This is our raw image. So those of you who look at the SNAP practicals will look at what's called SLC data, so single look complex data, and it comes in the radar coordinates. So these are it's the slant range and the azimuth direction, which is just the pure radar coordinates, not geographic coordinates. Let's look at something similar maybe to the one in the middle here. So this is an extreme case because there's actually shadow on the back of this pyramid. So on the near side of the pyramid, we're viewing it from the left here. The near side of the pyramid, so I've cut out the section from the previous image just so you can see what I'm relating it to here, is that you've got some foreshortening here so it doesn't completely lay over, but that whole face of the pyramid has been squashed up. If you view it from the other direction, that same pyramid will look like it's leaning the other way. So it's just the exact mirror image of what's happening. But to explain the kind of processing that you want in a radar, I'm going to take a case that's not quite as severe. So it's not radar shadow. The pyramid is a bit less steep. So you're actually getting a signal from the back face of the pyramid. It's just not as bright. And this is the ascending case and that's the descending case. So you'll see it leans. The foreshortening means that the pyramid looks like it's leaning towards the sensor. Now, in the terminology of SNAP, what you'll find is that you can do what's called terrain correction. And what this refers to is that we're now actually put the each of the pixels in this radar image and we'll put them into their proper geographic location. You might refer to it as an orthorectification if you like. But you'll notice that the base now is square, whereas it was rectangular in the instance here in the slant range data. So we've got it in, so that's reassuring. It's in the right, it's the right proportions now, so they're in the right proper geographic location. And the pixel that corresponds to the peak is in the center of that square. So this is what you would expect to see as a planimetric view of the pyramid, so that each point is now in its proper geographic location. But you'll notice that we've done this. There's two things to notice here. One is that the pyramid is all made of the same material. This is what we're assuming. And I'm assuming here that the pyramid is made of the same material that's all around it. Maybe they're all covered in grass. So maybe this is some very regular grass-covered pyramidal structure in some park. However, after we've done the terrain correction, you'll notice there's still, it still looks like it's being illuminated from the left. So this side on the right here is darker than this side, which is very bright. And they're both, that's brighter than the two sides. So it's not been properly adjusted for the changes in the incidence angle. The other thing is that this area of foreshortening it's maybe only 3 pixels, but these 3 pixels are now stretched out to make sure everything fits. So it might look like you've got 2 pixels worth of data here, but it's actually the same. It's the same value that was in the middle pixel here. It's just been stretched out over 2 pixels. So you may get an orthorectified terrain corrected image like that, but be aware of the fact that the slope might mean that your actual spatial resolution on the upside versus the downside or other slopes may not be the same. It might be slightly different. Because in this side, in fact, we might have many pixels that make up the backside of the pyramid, and they've all had to be squashed up instead of stretched out in order to account for that, the adjustment of the orthorectification. Now, the other thing is that what you can do is what's called terrain flattened. And terrain flattening, you have to make a big assumption here, which is that you know what the relationship is between backscatter and incidence angle. So part of it is that these pixels are all bright here for 2 different reasons. Okay, these pixels are bright. One reason is because you've got a very small incidence angle. You're looking much more directly towards the face of the pyramid, whereas on this side you're only looking at it in a very shallow angle. But you've also compressed all of the scattering that comes from this plane is being compressed into a smaller number of pixels than this plane. So there's 2 different reasons there of why the near side of your, or the slopes that are facing towards you end up brighter. And a full terrain flattening will take into account the fact that you've stretched out these pixels. It will also take into account the local incidence angle, and it will make an assumption about the trend in incidence angle versus backscatter, and it will actually try to correct these values so that the values are a better reflection of the actual average backscatter from that particular area of ground. So it's a very optimistic case I've drawn here, which is that all four sides now look the same, and they look the same as the surrounding signal. So if they're all in grass, you would hope that they would all have the same backscatter that corresponds to grass. But in actual fact, we have to be aware of the fact that there's been made some assumptions in there, and that's not always the case. So one of the key things to note is that, for example, in terms of analysis ready data, Google Earth Engine and Earth Blocks both have got terrain corrected imagery, but they don't have terrain flattened imagery. So you will still see, it almost looks like it's a side illuminated DEM, because it's still got brighter upside and downside. And you'll also see that when we look closely at them on Wednesday, is that visible? That's not visible. If you look closely at them on Wednesday, we'll see it actually, you see, it looks like it's been stretched out. You can see these areas that have been almost like they've been elongated, and they're visible in the data because they've been geo-corrected. In Snap, you can do the terrain flattening, and you can go the full hog, and you can take a look at and see how that compares. But also, so this is some data of Glen Affric. Some of you might have had the pleasure of going to visit Glen Affric. My sister and family live in Cannock, near the end of Glen Affric. So when we did this campaign back in the early 2000s with DLR's airborne SAR system with L-band data, that was very convenient. So we all crashed at my sister's house, basically. And because it's Scotland, we had a lock-in at the local bar till the early hours. But what I'm showing you here is just the difference between the projected ground range versus the slant range. As people who are interested in the applications, we want it into its proper geographic coordinates. And you just have to be aware of the fact that you will get variations and distortion because of the slant range. And that's the data that your something like single look complex data will come in that slant range format, not the geo-corrected. And I'll talk about that at the end of these slides about the different types of data formats. And this is the same data, but it's properly geocoded, so it's properly terrain corrected. But you'll notice it's not been terrain flattened. So the slopes that are facing towards the system, so the upside and the side of the loch, for example, they're all brighter than the downslope of the as viewed from the aircraft. Apologies. I've got it off mute because I'm using it for the metronome. Now, in terms of the topography, the impact it has on topography is quite significant, but I realize that some of you are interested in looking at vegetation and trees in particular. And so one of the things that you have to be aware of is that this effect of the layover is also an impact on tall structures like trees. So these aren't trees, these are electricity pylons. But you can see that there is an actual image of the pylon. The pylon is located here. That the image of the pylon lies over, it leans over, just like the mountains are leaning over. And you can see the shadow of the pylon is at the back there. And so one of the things that you have to be careful of is if you're making a ground plot that looks like that, your tree may lie within your ground plot, but a large part of the image of the tree may lie outside it. And that's maybe not a problem if you've got lots of trees and they're all very similar, because the trees over on the right here will be leaning over into your plot just as much as these trees are leaning out of the plot. But it is an important thing. It's important to take that into consideration. So this little animation here just shows you instead, this might be more relevant to some of you looking at vegetation, which is that, well, the backscatter that comes from the canopy is coming back at a different time from the backscatter from the from the ground. So it's important that you understand that this geometry is problematic, and just to give you an indication, is that if you're at an incidence angle of 45 degrees, then with a 20-meter high tree, is that the top of the tree will lie in your radar image 20 meters closer to nadir than the base of the tree. So it will look like it's lying down and 20 meters long. If you go to smaller, 45 degrees incidence angle is actually quite large. For a satellite system, you're probably more closer to 20 to 30 degrees. And so in fact, a 20-meter tree will actually look even longer on your image. So I've shown you this plane in terms of the range direction. And what I'm going to do is, hopefully, if this animation just works, if I do that, you get the idea now that we're now looking obliquely towards the ground surface. This is my satellite. It's a Lego version of Sentinel-1 that I made. Its direction of travel is up the top here. Let me just get my drawing. So we've got our direction of travel up the top. This is our nadir. So nadir is the point directly below the satellite. So this is the flight, the track on the ground of the satellite. And this is the beam that is projecting down onto the surface. Now the antenna, if the antenna is only about 1 meter long, it has a much longer beam pattern on the top than it is wide, because it's 10 meters or so wide. So it's 10 times wider. So we would expect the pattern that appears on the surface, the patch that we illuminate, is roughly in the same proportions. So it's roughly going to be about 10 times longer than it is wide. So our slant range direction is directly from the satellite. We have our ground range direction, which is actually on the surface. And this is what makes up our swath. So that's our swath width. And we call the along track direction the azimuth. So the azimuth is the term that we give for the along track direction. So I'm going to give you a little bit of an explanation for how we actually build up the image in the azimuth direction, or why that might impact on our interpretation of imagery. And then I'll go back to a couple of the challenges to do with the fact that we send out lots of pulses. Now, what we really want is a really narrow pattern on the ground here. If we could make this pattern so that it was really narrow, we could essentially do something like a push broom scanner, and we could just scan along here with a very narrow beam. So we could make, if we could only make that, say, 30 meters in width, then we'd have essentially a nice push broom scanner system, and that would solve our problem. We get nice 30-meter resolution images. But as I mentioned before, in order to, if you do the calculations of your wavelength over the size of the aperture, in order to get 30 meters down here, we need a few kilometers up here. And we're not going to fly an antenna that's a few kilometers long. So I'm going to give you one explanation. There's at least 3 explanations you can give for how we do this aperture synthesis. So how do we synthesize this larger aperture? And one of the explanations is really Doppler beam sharpening. Another explanation is to do with the phase measurements that we make. And so it's just a geometry question. And a third explanation, which I'm not going to give you today, is to do with building up the image with lots of, it's the one I mentioned last week. You have lots of small antennas and you fly them consecutively together to make one big antenna. In actual fact, all of these explanations are identical. It's only in terms of the language and the way that you express the mathematics, but they all end up telling you the same thing, and they all really mean the same thing. But today I'm going to give you one explanation, which is if we look in plan view now, is that it's to do with how do we extract information out of this beam. So we're now looking down on the satellite. So the nadir point is directly below this satellite, just under here. Our satellite is here and it's moving in this direction. And it's sending out its beam down to the Earth's surface obliquely, but because we're looking at it in plan view, we don't see the height that the satellite is flying in. But we're interested in what happens down here. So there's our beam width there. We've got our ground range direction and we've got our azimuth direction. And that's an indication of our swath width given by how much of an area we've got a patch on the ground here. So let's zoom in onto that beam. And let's see what's happening in a bit more detail here. So this footprint of our illumination on the ground is that what we're going to do, one thing that we can do is we can just draw on here the lines of equal range. So the distance across the ground is approximately related to the distance, the timing of our echo coming back. So each of these lines you can think of as representing, or in fact, each of these boxes you can think of as representing a range bin. So that this is all the echoes that come back in this bin here get put into that pixel. All the echoes that come back in this time period get put into that bin. Now you notice I've drawn it with a curve here, and that's kind of exaggerating the fact that we've got a center point, but there is an angle. So there is a curvature to that pattern. It's not, they're not exactly straight lines. I've exaggerated the curvature because the center of the circles are further back here. But at the edge of the beam, you're slightly further away than you are at the center of the beam from the radar system. So imagine essentially we could have a bit of string. You could get, or I'm just going to use this as my example. But we could take a bit of string like that, and you would just draw out the little arc on the beam pattern that at that range, all of the echoes come back at that same time because that's the same distance, and it would carve out a little curvature rather than a straight line. But the other thing that happens, and I've got a little animation that helps illustrate this, is that when the signal comes into the beam, it's slightly traveling towards us compared to when it goes out of the beam. And so a target, as it moves into the beam and goes out of the beam, under the echoes that we receive back from it, essentially undergo a Doppler shift. So they go from so that we can end up with, we can also plot on here lines of equal Doppler shift. I'm going to show you the animation and then come back to that graph. I've just extended the size of my footprint here just for illustrative purposes because I've got a little animation. So here's our target. It's not the target that's moving, remember, it's us that's moving over the target, but we're scanning. And this is just showing you the echoes that are coming off of this target. So let's imagine that it is it's a church in the middle of some agricultural fields. So it's a nice strong scatterer, and it's giving us a good response. And as it comes in, arriving, so our satellite, if you remember, we're actually moving. We're traveling in this direction. So if we're sitting on the radar system, this moving target, or this target looks like it's moving, even though the target's stationary, it's actually us that's moving. But as the target first comes into the beam, you'll notice that if I draw in some of the wave fronts here, as it comes in, is that the signal is a slightly higher frequency than if we look at what happens when it's going out of the beam. Where the frequency is much lower. Now the waves have been spread out. And remember when we looked at the key concepts, we looked at the idea of the Doppler shift. So this is the Doppler shift in action here, is that the echoes from this target as it first enters the beam have a higher frequency than when it exits the beam. That's what the echoes look like to our radar system. So if that's the case, what we can do, we can actually plot out lines of equal Doppler shift. And so even though the width of this beam here on the ground might be many kilometers, we can actually separate out the signal into smaller chunks based on whether it's blue shifted or red shifted, or has no shift at all, the zero Doppler line, so that we can then tease out our signals down to something more like the 10 meters or so that we're looking for most land applications. Now, this is, strictly speaking, this is Doppler beam sharpening, and it's a very common explanation for how we take a very wide footprint, so many kilometers, but we can carve it up into smaller pieces that we can make sense of in terms of small pixel sizes of 10 meters or so. Some of you will be happy with that, and you can rest easy at night knowing that that's a fair explanation of what's going on. Some of you might be less happy with that, because what you realize is that, well, this is coming over multiple echoes coming back. It's not a single single signal. And also, if you speak to a radar engineer, they will say, oh, the Doppler shift is so small, we can't actually measure the Doppler shift. And you'll get confused. And in my book, I try to make an explanation that reconciles both of these things. But what you'll find is that what is really measured is less to do with the is less to do with the frequency shift, but the fact that it has a very small extra distance to travel that introduces a phase shift. So as you look at the signal as it goes through the beam, it actually goes through a phase shift. Well, it starts off with a larger phase shift and then goes through a 0 and then ends up on a similar phase shift in the other direction. And if you remember, one of the things that I said right from the beginning is that what makes radar systems different is that we measure the amplitude and the phase of the wave. So it's because we measure the amplitude and the phase of the wave is that we can actually extract these very small changes in the echoes coming back and the small phases that are a consequence of the geometry that's shown here. Now, the good thing to note is actually these things are reconciled because the definition of a Doppler shift is a rate of change of phase. So in actual fact, while we measure the phase, it is what we're measuring is essentially the changes in a consequence of essentially the Doppler shift, the fact that we're moving and the target is passing through this beam. So there are multiple ways in which you can interpret that, and it's the key thing is though that we can analyze, we can make these measurements in such a way that we can artificially produce a very, very narrow beam. So although the physical size of the beam is many kilometers, we can artificially produce a beam that is or a synthesized beam that is down to 10 meters or so. Now, one of the assumptions that's in here, and it helps, this is where the Doppler shift helps in terms of understanding what's going on, is that if your target is actually moving, then you introduce an extra Doppler shift, which your system will interpret as being a geographical location. It will put it into a different place. And that's what we see when we look at ships in the ocean, is that these ships, where you see the ship is displaced from its wake. So the wake is in the correct place, but the ship, because it's moving, is actually adding an extra Doppler shift. And so it gets put into the wrong place in the beam. But the good news is that, well, if you measure that distance, you can actually make an estimate of how fast that ship is traveling. Right, so that's the complexity of the azimuth direction. And the azimuth direction is very clever and fascinating. There's a few other problems that come in that we don't have time to talk about today in terms of how you trade off the spatial resolution on the ground in azimuth. And also some of the weird things that come out as a consequence of the mathematics is that the size of the antenna, you actually get better azimuth resolution as you make your antenna smaller and smaller, which seems completely illogical and opposite way around. And there are practical limits why you don't make a very tiny antenna, but it's not that far from the truth in terms of when you start to look in detail of the radar systems and how large their antennas are and what they're doing. Now, there's one other thing. So in the range plane, so we're back to looking at the radar system flying into the board or out of the board and looking off obliquely to one side. So we're looking side on here, and we're looking along the direction of travel. there's one other thing that we have to take into account here, which is that while we have a very strong beam down the middle, we also have these what are called the side lobes, is that we have very not very sensitive parts of the antenna pattern, which means that a small signal will also end up going into these small side lobes. And for the most part, it's not a problem, but it is a problem because one of those side lobes will be approximately pointing closely towards the nadir point directly below the sensor. And that's problematic because that even though the sensitivity of this side lobe here is very, very low, so it's not sending very much energy in that direction, and it's not going to pick up very much energy that comes back. But it does pick up a little bit of energy. And if it's looking directly to nadir, the problem we have then, if you remember, is that if you've got, well, let me give you an example that would be an extreme case. Imagine that your system is flying over some water here, and you're trying to map some land surface over here. Is that the land surface might not have very good, might not have a very large backscatter because the signal's coming in and it's scattering off in lots of different directions. So the signal might come in and it's quite a rough surface. It's also further away from the nadir point. So it's dropping off in energy because it's got further to go before it comes back again. And at nadir, this low signal is hitting a very flat surface, and so it's going to give you specular reflection that comes right back. So although this signal might be very, very low, it might actually end up in a very bright signal because it's pointing directly to nadir. So we have to get rid of that. And the way that we handle that, we do something quite clever, which is that we just time it. So whenever an echo comes back, whenever the echo comes back from the nadir point, that's when we're going to transmit another echo. So we'll just transmit an echo every time the nadir echo is due back, and we'll not have a problem. Except we do have a problem, and that's the issue of coverage, because we send out multiple pulses. So this is our pulse going out. Just draw that. That's our pulse. Let me stop that before it gets really annoying. That's our echo coming back. So this is time along here. But in a radar system, we don't wait until we get the echo back. We transmit out multiple pulses. So we're going to transmit out. This is a simple case where we're transmitting the second pulse before we've received the echo from the first pulse. But in actual fact, we might transmit many pulses before we receive the echoes from the first pulse. But just to illustrate how complicated it gets, is that here's 4 pulses, 1, 2, 3, 4, is that we have to make sure that the echoes fit inside the gaps of the pulses, because we can't be receiving an echo coming back when we're sending out a pulse. And we have to be careful we don't have extra signals that go on beyond. So this signal up here, I'll color code it in red. This extra little echo that is coming back late actually ends up in the echo that's associated with a different pulse. So it gets overlapped with echo number 3, whereas it's actually still part of echo number 2. And if we actually plot, so what you can do is you can plot out all the areas for different PRFs. So the PRF is the difference between this. So the rate at which you send out pulses, that's your pulse repetition frequency. Is that we can map out what it looks like. So I'm going to just annotate this graph in a second. So this is our ground range. And this is changes in PRF. So if we change the PRF from, say, 1200 to 2400 hertz, right? And I also want you to get an idea of what 1000 hertz sounds like. Ooh, hang on. That's 2000 hertz. So this is just to give you. I'm not sure how good the audio is that actually will transmit that, but I'm hoping you can hear a signal, which is essentially sounds like a constant note, because the frequency 1000 hertz is actually really high. And that's an indication of just how fast the pulses are being sent out from a radar system, is that it's in the scale of thousands of hertz. Now, if we transmit in hertz, there's two sets of colored lines here. One set of color lines is where the echo from nadir will come back. Okay, so they've got one set of lines where that at any given PRF at a specific altitude, so you have to define the altitude of the satellite, is that we'll get echoes that come back, and you'll notice that it changes in location. For any given PRF, it changes in where on the ground these signals are coming back from. And they, if I rotate this round, which hopefully, so you get a better idea maybe of how things are going, is that as we send out these pulses, when these echoes come back, right? If this is one pulse, this animation has only got one pulse that's being sent out. You need to imagine that we've now got a PRF where we send out multiple pulses. And if you send out multiple pulses, there are points that will come back across the swath that correspond to points where we've got echoes coming back from nadir. There are also points across the swath that correspond to when we're transmitting a signal. So if we choose about, let's say, 2000 hertz here, these patches, these red marks that I've made across the swath, so across the swath here, each of these bits on the ground marked out by the red lines, those bits of ground across here can't be measured. At that PRF flying at that altitude, you won't be able to measure those patches on the ground. So that's problematic. It means that we can't get these nice wide swaths that we really want to get. So we have to do something clever here, which is we have to change our PRF. So the one thing is that we're only going to choose PRFs where the nadir return arrives back at the same time as you're transmitting a pulse. So there's a set number of PRFs that we can use whereby you've got that overlap. And we're going to, and that gives us a bit more space in which we can image swaths. But we're also going to have to change our PRF because we're going to try to fit into these, we have to try to fit into these gaps, but we're going to try to get larger coverage across a wider swath. And in fact, if you look at the images that you get, so this is the image, the standard image that comes from the Sentinel descriptors of what it's doing, covering across the Earth's surface, is that, and let's just look at one of these just now, which is the interferometric wide swath. You'll notice that it's trying to cover 250 kilometers. That's what it says the swath is, but it's actually made up of 3 subswaths. So it's not just, it doesn't make the 250 kilometer image at once. So what it does is it actually builds up a collection, and when you look at and Snap in particular, you'll be able to see the specific areas where it's picking up these 3 individual swaths. And what it's doing, incredibly enough, is actually, if I draw in here, it's trying to choose a particular PRF. So it might choose a PRF here to do this part of the swath, but then it chooses a different PRF, say around, no, where do I want to choose it? Closer to there, to fill that part of the swath. And then it might come back to choose another PRF to fill this bit of the swath. So essentially what it's doing, what the radar system is doing, is it's switching, it goes along and it collects some of the data at this PRF. Then it changes PRF to collect the second swath. Then it changes the PRF to collect the third swath. And this is what's called the, what he's referring to as TOPS, the Terrain Observation with Progressive Scans SAR, TOPS star. So this diagram is a kind of complicated way of trying to illustrate what it's doing, is that it's essentially scanning this subswath first, then it's scanning the next subswath, then it's scanning another part of this swath, and then it's scanning the third swath. And when you actually look at the data, and especially if you follow the practicals in Snap, is that you'll see you can actually visualize it as these three chunks. So what you'll see is these are the three swaths. So these have each been collected at a different PRF in order to fit into these gaps. And there is a black line that appears between them because that's just the separation of the individual data collection. If you actually zoom in, you will see that they repeat each other. So there's a bit of a repetition. So in actual fact, that isn't a gap in the data. That's just a separator of two patches that can be overlapped to stitch it together. And likewise, it looks like there's a gap between each of these swaths, but in actual fact, there's an overlap. So that bit there overlaps with this bit here. And so part of the processing that you go through in processing the radar data in Snap is that you stitch these together, and you actually merge all these individual subswaths together to create one large wide swath image. And that's how, if you're looking at the Sentinel strip map, it's a nice narrow 80 kilometers. It fits in. They can choose a different elevation beam, but it's just one beam, and it fits into one of those gaps in that graph. Whereas if you're looking at the interferometric wide swath, to get the 250 kilometers, it actually needs three subswaths that it does at the same time to create that. And if you look at the extra wide swath, it actually has 5 subswaths. So it's doing the same processing of changing the PRFs around in order to stitch these together in order to create that large 410 kilometer swath, because it would be impossible to actually achieve a 410 kilometer swath with just a simple imaging. Now, what I'm going to do, there's two things that I've left to cover in terms of the slides, but they make a perfect segue into the practicals with Earth blocks, because we're going to look at the range resolution and what that constitutes. So we'll actually look at some specific examples of how the resolution might vary, or how does it compare to other things. And the other thing I want to do, so there's only a half dozen slides or so left, but it's 4 o'clock, so I'm going to finish. The other thing I want to look at is just about the SAR images, and in particular, the impact of speckle. And in fact, it's best, it's easiest to do that when we're looking at Earth blocks, because what we'll be able to do is actually look at the impact of speckle and the variation in speckle as a consequence of, well, what we'll do in Earth blocks is average over time. So we'll make lots of averages. But so it's a half a dozen slides that we'll look at in the, half a dozen slides that we'll look at the beginning of Wednesday's lecture, but we'll do that while we look at some Earth blocks examples.